Good morning and welcome to this latest installment of Mazzetti's Bending the Climate Curve Learning Series. I'm Christina Vernon Sanborn, Sustainability Practice Leader here at Mazzetti, where bending the climate curve is our mission. This morning, we'll explore smarter controls for sustainable, resilient hospitals. Next. I'm really excited to share this one. We're going to talk today about Advanced Direct Digital Controls, DDC, which are the hidden engine behind driving hospital sustainability, resilience, and cost savings. By optimizing central plant sequencing, fine-tuning airside systems, and integrating renewable energy and emergency power, DDD strategies can reduce HVAC energy use by 10 to 30% while maintaining patient safety and comfort. These systems also simplify compliance reporting, like for LEED or Title 24 or carbon mandates. They improve resilience during outages by prioritizing critical spaces and enable predictive maintenance to extend equipment life. For hospital owners and operators, investing in smart controls is not just a technical upgrade. It's a pathway to lower operating costs, reduced risk, and stronger positioning as a leader in healthcare sustainability. Joining us today are Kevin Bostaff, Chuck Wales, and a special guest, Jim Crabb. Kevin is a mechanical engineer here at Mazzetti and focuses on the healthcare, mission-critical, and science and technology space. His work reflects a commitment to people and the planet, emphasizing sustainable design to create environments that support healing, productivity, and well-being. Kevin considers every project's unique priorities, including energy efficiency, usability, reliability, and costs, to achieve balanced, high-performing outcomes. Chuck is a senior commissioning authority here at Mazzetti, with over 30 years of extensive experience in controls, HVAC, and central plant systems. Chuck's a seasoned commissioning expert whose deep-rooted expertise stems from a diverse career as a contractor specializing in HVAC, plumbing, boilers, and controls, as well as roles as an operator, project manager, and commissioning agent. He has a proven track record in designing, installing, and commissioning and operating highly efficient building systems, and his hands-on experience equips him with unique insights into what works best in various scenarios, ensuring optimal performance and sustainability. Jim Crabb is a senior mechanical engineer at Mazzetti and led the engineering teams that designed the first 2 hospitals in Georgia that used recovered energy for all building heating and hot water production. One of those was the first in the state to receive gold certification under LEED for Healthcare. He also contributed to 2 editions of the guidelines for design and construction of healthcare facilities. Most recently, Jim has led Mazzetti's response to designing COVID hospitals in underserved countries in coordination with the International Federation of Healthcare Engineers and the World Health Organization. I think you're going to really enjoy hearing from these speakers. Now, next slide. The learning objectives today focus on how DDC contributes to hospital sustainability and resilience. We're going to learn how to quantify the potential energy savings and operational benefits of implementing DDC strategies. We're going to identify compliance and reporting advantages and discuss how DDC enhances hospital resilience and supports predictive maintenance. Next slide. Today, before we get started, a bit of housekeeping. Today's event qualifies for 1 AIA Health Safety and Welfare CEU. If you didn't provide your AIA number when registering, please send it to info@mazzetti.com. We will hold questions until after today's speakers have made their presentations, but you are encouraged to ask your questions at any time during the presentation via the Q&A function of the webinar. Today's session is being recorded, and we'll share with you the PDF of the slides, as well as a link to the recording after today's event. Okay, with that, I'm going to turn it over to Chuck. Chuck?
Thank you, Christine. I appreciate it. It's a pleasure to be here and to be presenting with all of you. I've lived controls for most of my adult working life, and it's a pleasure to share some of the information with you. So I want to start off with some of the effects of climate change. Whether or not you agree with the causes, the results are evident. Some of the pictures here from Superstorm Sandy, Hurricane Katrina. We all know the effects that are happening currently with our weather. That's affecting hospitals in a lot of different ways, of course, with driving shifts. There's one article from the UN that says that 1 in 12 hospitals around the world are at risk of being shut down by climate change disasters. And, but from my own experience, I grew up in Los Angeles, Orange County, and one of my customers was the Directors Guild, and the Directors Guild had this picture of the Hollywood sign, and there was a layer of smog across it. And I remember when I was in grade school, we used to have smog alerts, and you had different levels of smog alerts. Like level 1, you could go outside, but you couldn't run, and level 2, you couldn't go outside at all. And we really made a lot of headway when it comes to air quality, but we just have a lot more to go with carbon reduction. And so we'd like to talk about how controls affects that, and the things that we can be doing to affect the change. So this is a basic DDC infrastructure. We're going to kind of go through what DDC is, how it interacts with your building, some of the advanced processes that are being connected to DDC now, some of the history of that, and then we'll open up for questions and answers. Jim is one of our special guests. He's going to be talking about energy, and Kevin is one of the controls designers here at Mazzetti that's going to be giving us some insights onto their work the wonderful work that they do for designing controls. So the basic layout of a DDC system is you have your sensor or actuator level. This is where the equipment lives, down at the first level here. Second is the floor level controllers, where you have the controllers that are interacting with all of this. You have an integration level where it's all pulled into a master controller, and it gives you the readouts and sometimes the graphics. Oftentimes this gets cut into a server, where the server is displaying your graphics and giving your scheduling. Gives your operator interface or management level, if you will. This is the basic infrastructure of a DDC system. Now, nowadays, we're not using the MSTP or excuse me, the RS-232 as much as we're using IP, and I'll get into that a little bit later, but I do want to point out this LAN right here. BACnet and LAN are two protocols for EMS that are typically on the RS-232 or the 2-wire bus. LawnWorks is no longer being supported. Echelon quit making their Echelon chips. They're going to be at end of production probably by next year. So if you have a LAN network in your system, you're probably looking at doing some end of life changes here. So the history of the EMS systems, I got in the beginning when we were doing pneumatics. So I hate to date myself here, but yes, I was in the pneumatic era. In the 80s and 90s, we had a proprietary era where the big three were basically controlling the market share, and they still control the market share today. That's Johnson Controls, Siemens, and Honeywell. 2000s, we got to BACnet from ASHRAE, and open protocol adoption started getting more popular, and more of the big three started adopting these BACnet and IP strategies. 2010s, Niagara came out, and it actually came out in the early 2000s, or late 90s actually, but started getting popular in about 2010. Honeywell actually purchased Niagara, which was Vicon at the time, back in sometime in the early 2000s, I think. And it's still marketed under a lot of different white brands. They white label it to almost every OEM that's out there now. And then today we're really getting into advanced, cloud cybersecurity enterprise integrations, and this has really kind of been an exciting time for controls, but it's also a confusing time because there's a lot going on, a lot to know. So your basic level controllers are in a couple of small groups. So you have application specific. This, for example, is designed to do a VAV box, and that's typically all it does. Then you have a universal controller. You can put any kind of input and output and logic into this controller, and it can serve a wide variety of services. Some of them will have graphic interfaces on the front or some type of a control panel, so you can do local, remote control, which is really helpful for your operators. So if you're specifying these are helpful. Expansion modules, this is something you need to know if you're actually in the weeds like I am. Expansion modules don't have any smarts to them. They just typically expand off of one of the other controllers that does it capable of doing logic. I have seen vendors use these for I/O with the logic coming from some other controller. This is kind of a weak link. So one of the things you want to know when you're designing a system is what happens if you lose communication. So typically I want an entire system that's going to be off one controller. It's making all the decisions, it's providing all the logic. I'm telling it what I want it to do, but if for some reason it loses communication with me and my computer, I want it to keep doing what it's designed to do. These are supervisory controllers. Supervisory controllers are at the top of that chart I showed you earlier. So all of the I/O from the field come into these devices, and these devices make decisions for scheduling. Sometimes they'll serve up the graphics, but oftentimes that goes to the server. These are become really robust. They're made out of a lot of different things nowadays. There was times where they were putting XP in a box and doing all kinds of crazy stuff. This Distech here is actually a Niagara controller that's white labeled Distech. The same with the Facility Explorer right here is a Niagara controller. These are basically the same thing. It's called the JACE, or Java Application Control Engine. This is Tritium's product, the same thing. Metasys has the same look and feel of a lot of these devices, but they have their own operating system. And you see Johnson Controls here and Johnson Controls here. The Metasys line is limited to the branch and certain select what they call ABCS, or Authorized Building Control Specialist vendors. The Facility Explorer line is from a different group of integrators. And so oftentimes you can get a mix of flavors from the same company or the same manufacturer that are set by different controllers. The advantage to this is that there's some geographies that don't have the scale of large cities where you have your choice of bringing in whoever you want to control your building. But I would say I'm not going to give preference to any particular vendor. They're all very viable these days. All of the controllers are viable, and I think you're really your vendor is the one who's going to dictate your success or failure. So this is an automated logic network. This is oftentimes what you're seeing now with new buildings. And the part that I'm talking about is that everything is IP these days. So including the VAV boxes, you have a daisy chain VAV network that goes into the ceiling. So you don't have to run everything home run back to your LAN or your network room. You can just basically daisy chain these controllers. Now, when I say daisy chain, the controller has to be designed for that and has to have dual ports. There's some logic called spanning tree technology and whatnot that the IT department uses. The devices have to be designed for that, but at least you don't have to home run things. The RS-232 that I was talking about earlier, MSTP is the most popular for BACnet. That's a 2-wire system that daisy chains. If you have an old Johnson Metasys system, you're probably at 9600 baud. That is a very slow network, but it's doable. Nowadays, you can get the RS-232 baud up to, I think, 232 megabits, but probably 115 is probably more common. And your equipment all can integrate into this equipment via either RS-232 or IP nowadays. So all of your devices information is online. Your controllers are all online. And ASHRAE has come out with a new security standard for BACnet. This is probably going to give people some headaches, and I don't want to talk against it because it really is a secure protocol. But the problem I've ran into when you have high security inside of the network is that things like managing the licenses. If the license expires and nobody's keeping an eye on it, guess what? Your network goes down. I've seen that a few times now. So my suggestion is first talk to your IT professional. Make sure they island this entire network. I would recommend that before we start making security inside of the network itself. Just make sure it gets properly firewalled to the outside world. Everything is getting connected nowadays. You can see right here, most everything from the DDC system goes up to one central server and or a remote switch that's handling the data that's passing through the firewall. And then oftentimes your services are on the other side of that firewall. This is just quick brief of IP network configurations I was talking about earlier. Daisy chain is by far the most common nowadays, and home runs are also prevalent to your major controllers. When I talk about ring topology or hybrid topology, that's where it is going in a circle. The controllers need to be designed for that. And again, you have to have spanning tree technology from your IT departments. It's called RSTP or MRP. Because if you put these in a loop, which helps if you lose one side of the connection, you don't lose, like here, if you lose your connection, you're going to lose this whole side of the controller network. So this helps if it supports it, but it has to support it, and the IT department has to be involved in that. I certainly encourage you now to get IT involved in all of your projects that involve DDC. It's come a long way. Okay, we're going to move into energy, and I know I'm going through these slides quick, and I apologize. I only have so much time to give you a lot of information, so I'm going to do the best I can. when I taught air conditioning, the first thing I taught my class was the first law of thermodynamics, where energy is neither lost, it's neither created nor destroyed except for nuclear reaction. It's only transferred from one medium to another. And so that's really what we're doing with HVAC. We have our loads in the building, be it sun, electricity, people. We have to move that heat load from the building. We move it into the the air conditioning. Oftentimes the chill water system, the air handler puts it in the chilled water moves it to the chiller takes it, moves it to the condenser puts it back to the atmosphere, and that's the transfer that happens. To give you a quick example, when I first started commissioning plants or operating plants, our typical consumption was about 1.5 kW per ton for a chilled water plant. Today, we can create and operate a plant at 0.25 kW per ton. That's an 80% reduction. For an annual hospital dollar saving, that's $1.6 million if you have an 800-ton load. And I'm just going to quick plug here for the power curve for a VFD, and then I'm going to turn it over to Jim, who's going to tell us a little bit more about energy. This is the graph right here for a fixed speed pump, and at 0% load, it is still 60% power, and then the curve goes like this from flow to power. With a VFD, your curve starts down here at about 10% power with 30% flow, and then also caps out at 100. And I want to talk about this intersection here. It's a cubic relationship, and it's even more if you look at the affinity laws as far as the relationship between speed, pump, power, etc. But at 80% flow, for example, if you look up the curve here, excuse me, I'm at 50% energy. So the last 20% of energy takes 50% more power. Now, you can't just go to your VFDs and park them all at 80% effectively. Yeah, again, there's affinity laws, there's pump curves, and there's things you need to look at, and I certainly recommend you consult with your engineer. But one of the things we do when we're designing these things is we utilize variable frequency drives and other forms of efficiency to keep the systems operating in their optimal band. And for that, I'd like to welcome Jim Crabb, who's agreed to join us as our guest speaker to talk a little bit about energy and the energy flow.
So Chuck mentioned the first law of thermodynamics, that energy is never lost. And that's true on kind of a global perspective. Energy isn't lost, but on the building perspective, we do a lot of throwing away of energy. We discard it to the atmosphere. So this diagram is just kind of the perspective of a building. The box is the building, and we have all these different energy inputs. We know we have solar energy coming into our buildings. We have conduction from the outside in one direction or the other. And obviously, in cold weather, we're losing heat, and in warmer weather, we're gaining heat. But the main drivers of energy in our buildings are the electricity and the methane gas that we put into them. So the gas side, we all understand that we're putting gas into a boiler or something similar. Might be hot water, might be steam. In our hospitals, we're using that energy for reheat, sterilization, preheat, and some other uses. And I think it's pretty intuitive that we burn that gas and we're making heat, so that is heat in our buildings. What might be less intuitive to some folks who are not mechanical engineers is that all of the electricity that we put into our building also becomes heat in our building, all of it. So those computers that get a little bit warm, they're converting that electricity into heat primarily. We do useful things with it along the way, but it becomes heat in our buildings. And so our cooling system is designed to absorb all that heat. We run our chill water, we run our air handlers. The air handler transfers heat from the air to the chill water. Chill water goes to the chiller. Transforms the energy to a higher temperature, takes it to the cooling tower, and the cooling tower throws it away. We also lose heat through exhaust and make up air for outside air. So this is kind of the traditional way that we've done things. We've treated these as separate systems. We have the electricity, we put in all the power we need. We have the gas to make all the heat we need. We have the cooling system to remove all the heat that we don't want. But there is a better way. Next slide, Chuck. And that is to, instead of throwing away all that energy, take advantage of these systems that we have to integrate the systems and keep as much of that energy as we need. So we have this chill water system that runs around our buildings and picks up heat from the cooling coils. Cooling coils, of course, are absorbing that heat from the spaces. So we have this chill water loop that's running around and picking up all that heat. It isn't a very high temperature by the time it comes back to the chiller. It might only be 54 degrees or 56 degrees or something like that. But it still is heat. That water is warmer than when we send it out. That's its job. And rather than just raising the temperature, sending it to the cooling tower and rejecting that heat, we can reconvert that heat to a temperature that we can use. 120 degrees is a good temperature, 130. Some of our older systems are designed for a higher temperature, and we can accomplish those higher temperatures with heat pumps as well. It's not quite as efficient. But through this heat recovery process, we can recapture that heat, keep it in our building, use it again, and throw less away. And therefore, we're not having to burn gas to make the heat we need for our buildings. So that's kind of on the overall system level, we're trying to recapture that heat. Next slide, Chuck. So the thing to look at here, the yellow part, yellow or orange, whatever your screen shows you, is the heating load of the building. And the yellow part is the heat that we're taking out of the building with a cooling system. This is a typical building. I think this one is actually, this is not a hospital. This is an ambulatory surgery center in Georgia. And if we use a heat recovery system, we can convert as much of that cooling that we're removing into heat as we need. So the orange is actually representing all the heat that's available from doing that, and the red line is the actual heat load of the building. Now, in colder climates, it's going to be a little more higher line in the cold weather. But the red area is the only area where we actually need to add heat to this building. And there are different ways we can do that. But the key is all that other space underneath the red line we can do with heat recovery and not have to add more heat to the building. Next slide. And so the key to this is, again, in the old days with our pneumatic controls, and I used to use pneumatic controls too, we really had to kind of separate things. There was no way to really integrate all this stuff. A heating system was a heating system, and the sort of the height of control on a boiler is a mechanical linkage adjustment for the burner, and a chiller basically just kind of runs, and we reject all the heat. We treat these as all separate systems. But with these modern control systems, we can start to bring these things together and create a single plant that does both heating and cooling without bringing in any gas-fired equipment. So the color coding here, the blue part is the part that makes the cooling. The red part is the part that makes the heating, which also makes some cooling through heat recovery. And then for those times when we don't have quite enough heat, we have either the air source heat pumps, that's represented in the little green area there, that just add more heat to the building when we need it. Those can be very effective at even fairly cold temperatures, but sometimes that won't be enough. And then another approach is to store that excess heat during the summer and have it available to us in the winter. One way to do that is through a bore field. There are other types of thermal storage we could talk about, phase change materials, but the idea is to have that supplemental heat when we need it. And the key to making all that happen is, one, designing it that way, but also these control systems that allow us to integrate all these systems and basically reuse the heat that we already have available to us. And I'll pass it to Kevin.
Thank you, Jim. I think before we get to Kevin, I want to talk about if you envision this entire system and the orchestration that's required to make all of these decisions on which systems you bring on, when they bring them on, because you understand that oftentimes just turning it on isn't going to work. There are certain times that you have to turn it on, and there's only times where it's applicably where it's applicable and it's going to be actually save us energy. So thank you again for that great presentation. I've enjoyed all of your work over the years. I want to talk briefly about sequences, and then I'm going to pass it over to Kevin. That's going to give us a little bit more in-depth, on some of that in FDD. ASHRAE 36 has come up with guideline 30. ASHRAE has come up with guideline 36, which is a set of control sequences that are canned. And the intent of this is to simplify both the design, the construction, and the commissioning. And I'll get into an example shortly about why, one of the reasons we need it. But these are actual numbers they've come up with on a full retrofit site using these guidelines. They're getting these kind of savings from MOBs and office buildings. Software-only retrofits are getting smaller but appreciable savings. And the overall intent eventually, again, is going to be so that we can have a canned set of specifications. We'll have a canned set of software that's going to go in, and then commissioning is going to be simplified because we're going to know what the sequences are. And that's kind of the intent of monitor-based commissioning and kind of AI FDD, if you will. And then these sequences can be mixed and matched to put together. But the reason, if you're a commissioning agent like me, you run into these things in the field, and this is from an actual medical building that I commissioned not too long ago. And this building is monitored by an FDD system. It didn't catch this. And one of the things I caught here, what you're looking at is the graph of an RTU unit. This RTU unit is off right here. It turns on, it starts up. This is the hot water valve, the red line. The blue line is the chilled water valve. The purple line is the economizer. Green is discharge air temperature, and blue is chilled water valve. So it starts up at 3 o'clock in the morning because it's 37 degrees outside, and it needs to start up at 3 o'clock in the morning. Opens up its hot water valve, which is kind of expected, but the economizer was also fully open. And then half an hour later, it drops that and it turns on the chill water valve, which, by the way, starts the chiller. And then it changes its mind and says, no, I don't really need that. I need the hot water valve instead. But then it opens the economizer again. For those of you that don't know, economizer is your outside air dampers. And then you see the discharge air temperature coming up in reaction to the hot water valve. It figures out it's where it needs to be. It says, okay, drops those, opens the chilled water valve again, which restarts the chiller, and then drops that again, and then it figures out that it can kind of get some kind of a stable control. This is called a hunt, by the way, when it's trying to find itself using just the economizer. Now, what happened is you've lost from 3 a.m. to about 7 a.m. before it figured out where it was. You've lost a lot of energy and probably did more harm than good. And these are the things that oftentimes FDD isn't going to catch. In this case, it wasn't simultaneously heating and cooling. The FDD doesn't always know if the economizer should be open or not because there's outside air requirements. And so there's some things that just honestly need to be commissioned, not to do my own plug, but I just wanted to talk a little bit about that and why we have FDD in the first place and the importance of having good controls commissioning. So with that, I'd like to turn it over to Kevin, who's going to talk to us some more about some energy conservation measures.
Yeah, I just wanted to talk a little bit about some of the useful things we can do with these advanced digital control systems. One such thing is implementing a wide array of energy conservation measures. So things like supply air temperature reset, chilled water plant reset, and static pressure reset. These are strategies that look for a near optimum set point for central equipment. They can utilize ASHRAE 36's trim and respond logic in order to continually trim the set point at a fixed rate until downstream equipment starts to become unsatisfied. And that unsatisfied equipment can then generate requests. And when we have enough requests to exceed a predefined threshold, we start to reset those set points upward again. With those requests, we can also, we can log those. We can log those in a times requested counter, which helps operators identify certain equipment or zones that are continually restraining our reset strategies. So then that highlights to them equipment that they can go find an intervention for to free up the strategy and save energy. We can also implement things such as schedules like occupied and unoccupied schedules, where during unoccupied times, we can relax temperature and airflow set points in order to save energy. We can implement things such as demand control ventilation, where ventilation rates can be dynamically adjusted to control measured carbon dioxide levels in the spaces. We can do other things such as use occupancy sensors to override, even during occupied times, temperature set points and airflow set points based on whether or not we're determining that the zone is populated or not. You could really go on and on. The number of energy conservation measures that you can implement is really just restricted by your own imagination. Next slide, please. Alarm management and prioritization. This is another cool thing you can do with advanced controls. It allows you to manage and prioritize alarms based on what has the most pressing need and which alarms are of the highest priority. So it helps block out the noise from nuisance alarms and highlight the alarms that need immediate attention. One such method for doing that is creating an alarm suppression hierarchy. And an example of that is creating, let's say, an AHU system. You have an air handler that serves a bunch of terminal units. If that air handler fails, we're also going to see a bunch of alarms at all the terminal units. But those alarms at the terminal units are not where facilities' attention need to be. It needs to be at the upstream equipment. So by creating a system where those downstream alarms are suppressed, like all the alarms at the terminal units, we block out that noise and instead highlight that it's the air handler that is the critical issue for facilities. We can also assign different alarm levels that essentially do the same thing. We have different, ASHRAE 36 recommends 4 different alarm levels. You have life safety, critical, urgent, and normal. And those levels indicate to facilities how pressing of an issue it is, the urgency in which they need to generate a response, and the severity of the alarm. We can also tag alarms with things such as date and time, equipment affected, etc. And that allows for when there's a laundry list of alarms, facilities can sort through those to help them prioritize their responses. Alarms can be routed to appropriate personnel, and mobile notifications can be generated for critical issues so they're not missed. Next slide, please. Fault detection and diagnostics. This can range from the very simple to the very complex. On the simple end, we have things such as monitoring air filter banks for pressure drop. So you could install an air pressure differential switch across an air filter bank. And when that switch is triggered, it would generate an alarm to indicate that a filter is dirty and needs replaced. Slightly more advanced than that would be creating a rules-based fault detection diagnostic system, where something along the lines of you look at air handler fan speeds, and if the fans are at 100% and our static pressure set point is still not being met, you can trigger an alarm that indicates we have a problem here with the fans or the motors, possible blockage in the duct, maybe a problem with the set point itself. And even beyond that, you can go even more advanced now. You can create data-driven models that can help predict the performance of equipment. You continue monitoring the actual real-world performance of your equipment versus what is modeled. And when there is a difference there, it can indicate potential issues in the pipeline. So this allows you to proactively anticipate issues before they actually manifest themselves in normal operations. Next slide.
All right. Thank you, Kevin. I appreciate that. We're going to go into FDD and MBX a little bit more. These are some of the metrics that that we've talked about. I've got one more slide for Kevin that's going to be happening in shortly, so we'll be back with him. So FDD, these are some of the touted savings that are coming out of FDDs, the labor savings, the energy savings, and equipment savings, and no doubt that they can fix a lot of ills. A lot of times they're quantified nowadays, so they will give you savings that they report are happening by correcting the particular faults, and they have payback periods of less than 2 years. And so I want to throw another cautionary flag on some of this stuff, is that some of the feedback that we get from these applications are hundreds of issues per week that aren't real or actionable. It took months to map points and tune rules. We still don't trust it. We don't see measurable savings. Management isn't convinced. It gives us data, not decisions. We still have to investigate every issue, et cetera, et cetera. Now, this is because of the application. So I encourage you to methodically integrate these systems. And so oftentimes that people just, they see a nice dashboard up on the internet and they say, oh, that looks pretty cool. And they say, yeah, we can just plug it in and everything's going to be great. And next thing you know, the operator's getting 1,000 faults that really don't have anything to do with this day to day. And it's a good way to divide your facilities team. So I encourage you to approach these things carefully and methodically. One of the things that we do when we're talking about this is we set up basically a table and say, what do you want to get? There's a lot of good vendors out there and there's a lot of good systems, but they need to be coordinated first. And so ASHRAE 36 also has some FDD rules that go along with their guidelines. And that's okay for smaller facilities, but it's not really scalable. It's not an enterprise platform. And so I'd probably encourage most people to go with the enterprise route. But again, do that systematically. Put up a chart that tells what you want. And oftentimes one of the things is, do you have an energy manager? Do you have somebody that can understand these things, the analytics and whatnot? Because that's really going to depend on your success or failure in these with FTD. Compliance and reporting. DDC, we still have customers that want a dot matrix printer and want all of their flows and temperatures printed out every day. And I can't argue with that, but most of your DDC systems now will handle your regulatory requirements, reporting requirements. Lead 5 is going to require FDD for those lead points. And so just plan on that if you're going after lead credits. And I think did I miss a slide for you, Kevin? I think I might have missed a slide.
No, Chuck, you had them all.
Okay, thank you. Sorry about that. Okay, this is close to the last one. Everybody's looking at dashboards nowadays, and everybody wants to dashboard their systems. Everybody's pretty much always wanted to have their DDC online and have nice, pretty pictures. And a lot of times operators aren't as concerned about this, but dashboards happen in tiers. So your first level tier is your DDC or your field level. This is where your operators and technicians use it. FDD and analytics is the next level up. That's tier 2. Commissioning and energy engineers typically use that. And of course, the operators will use it also for fault finding. Energy and sustainability is level 3. Your energy managers, sustainability offices, et cetera, use that for maintaining sustainability. You have your C-suite level 4, and then your public facing if you have it with level 5. Oftentimes, 1 and 2 can be combined together, and 3 through 5 can be combined together. You don't need 1 and 2 to do 3 through 5. As long as you're getting your energy metrics from whatever reporting you're getting. Now, if you do have field measurement, then you will need to integrate with 1. But oftentimes, if you just have your utility bills and or your energy meters, and you can segregate that by whatever metric you're using, 3 through 5 is going to be there. Now, when you have a drift or you have a problem in level 3, then you're going to have to go to level 2 and figure out where your problem lies, and then go to level 1 to dive deeper into where that problem exists. And so when you're integrating these, I recommend that you start with level 1. Get your DDC correct, get your point naming correct, use the point naming conventions, Project Haystack, and there's also an ASHRAE guideline for that, for the point naming convention. That's also going to become part of ASHRAE 36. So get all your points naming convention together so that way your integration can be scalable. And then move on to your FDD analytics platform, and then your energy. Those of you that are still doing pneumatics, I'm sorry, but I will tell you that there are some DDC solutions for you. For example, I know it's very difficult and expensive to convert an entire floor of pneumatic VAV boxes, but there are some digital VAV thermostats that are pneumatic that will operate your VAVs and get you online, so you can at least have some visibility. And so start where you're at, get the major controller systems first, and then move up from there. Last thing I'm going to say in closing is that, and this is a slide from Niagara, of course, and I talked about Niagara a few times. Niagara has really made a lot of headway. I'm not touting any particular vendor at all, so I'm really agnostic here. A lot of people can do this stuff, and there's a lot of people that can put their name on this, what we call the full stack, where it's basically everything across the board. And I would say that just again, a word of caution, don't integrate something just because you can. There needs to be a reason for it. There's a lot of companies that used to do fire and security, and they pull all this stuff in together, and so you don't have fire and security on this stack right here. But it's okay to pull those in as long as you have need for it. Your operators probably need to know if there's a fire, if something's shutting down their air handler. Same with security. I don't really see a lot of use for it into your DDC system, but there might be some advantages to bringing in some data. So the good thing about integration nowadays is you don't have to have it all in the same computer. In other words, you can use BACnet, you can use other integration methodologies, you can bring in your lighting, you can bring in your data center information, you can bring in utilities, and those can just be integrated points that show up on your system and be part of your dashboard. So there's really it's endless, honestly, the possibilities, but I encourage you to structure these things carefully. Make sure there's a point of management for every system that you put in. And I'll tell you another experience I had is I was working for a college who had a lot of problems at the time that I started working with them. And one of the things they told me is they had a solar system up on top of one of their large buildings. It was a big solar array. And I put it in the back of my mind and went on to work on other fires that they had. And when I got back around to it, I said, let's take a look. Well, the system had been offline for more than a year. What they did is they made the solar panels flat up on the roof, and they just collected dirt and dust over the years, and the system just shut down. They didn't have enough voltage. So they've been running the solar system for a year with no production, and all we really had to do was wash the panels, and away they went. So the point is, you can't manage that which you don't monitor. So if you have a passive system like a solar system, and you don't have an active energy manager who's managing that real time, make sure that gets integrated into your DDC system so your operators can keep an eye on it. The last thing is that by the same token, when you have an energy manager and he's probably got 100 different icons that go to the different systems that he's installed over the years, if you lose that individual and you lose his access to his computer, you may have lost access to a lot of these systems. So make sure you have a plan to manage these things. So again, I want to thank everybody for their time. I want to thank Kevin and Jim especially for participating in this series, and I hope that we got something out of that. And I'll turn it back over to Christina.
Wonderful. Thank you so much. That was really rich with information. I would invite at this time the participants to enter any questions that you may have in the Q&A function. We're excited to answer your questions and your musings about this topic. And I'll start with a question about the future of controls. I know lighting has moved to wireless controls. And I'm curious if there's a movement to explore wireless controls for the building systems that we've been talking about today.
Yes, that's a great question, and thank you for asking that. Wireless has been around for a long time. It's had difficulties getting into the workspace because of the IT departments primarily. When you have wireless systems, you're basically opening your IT network architecture. So it's here to stay. There's a lot of applications for it. I think the IT departments need to be trained on the applications, and you need good engineering to demonstrate to the IT department that it's not a security risk. And so at some point they might get too much RF traffic going inside of a hospital, which is oftentimes not advisable. And so obviously initially they were able to affect pacemakers and whatnot. And of course you couldn't turn on your computer on your airplane at first, but I think that's come a long way now, and you're going to start seeing more advances in that as time goes on. And one thing I'll note is that typically when you have a LAN network on your DDC system, the LAN is completely physically isolated from the WAN, if you will. So that difference between the floor level and the field level controller is actually isolated, but IT departments aren't familiar with this. And so oftentimes they need to be educated on how those interact. Thank you for the question.
I would just add to that, Christine, and one of the most obvious things is to use wireless thermostats connected to your VAV controllers. I mean, how many times have we had to relocate a thermostat because it wasn't in the right place for Not because the engineer messed up, of course, but something went wrong, and a thermostat has to be relocated. Much easier when it's wireless.
I had a project where the thermostat was getting direct sunlight
Yes.
because of just an odd, at an odd time of day, a couple of, in a pretty narrow stretch of the year, and it froze everyone out on the floor. It moving thermostats is a really common thing.
Yes.
When you were talking, Jim, about storing energy, I know that, for instance, one of our clients, Stanford, has a pretty complex system that manages hot and chilled water storage, like actual tanks of
Large tanks.
large tanks. Can you talk a little bit about how controls need to change or be thought about differently if you're getting into thermal storage?
Well, good question. It kind of goes back to the integration of all these different systems. Once you add storage in the mix, once you add heat recovery into the mix, you really can't afford to think of these as separate systems anymore. When you add storage, you really have to think about, if you think about taking that excess heat from your chill water system and storing that rather than sending it to the cooling tower. Well, you probably want to store it at a higher temperature than what your cooling towers would normally operate at. So there's actually a cost to raise the temperature of that water to store it. So it's an important decision. You don't want to just always do that. You need to add some prediction into the need for that storage, and that means maybe connecting your control system to a weather service. It might mean some other strategies. In the case of borehole thermal storage, there's less of a decision to be made because you're storing at a lower temperature, and you always have a heat pump in the mix to raise that temperature to what you need it to use it at. But in the case of say a hot water storage tank, you need to have that hot water up at a temperature where you're able to use it. So you are paying a penalty to store. Plus, there's obviously loss when you store energy. So thinking about how you use that is important. If you're storing chill water, one strategy you might employ, in fact, is to when you need supplemental heat in the coldest weather, go ahead and make chill water as a way to generate heat. Those two things are really the same process. One side removes heat and then pushes it over to the other side. So that's another strategy that you can employ, and all of that takes intelligence. Ideally, it's all these control sequences that get written. My experience with writing control sequences is it's not really possible to think of all the possibilities, at least not for my brain and the people I normally work with. I hope that one day there will be AI capability built into these systems that will actually help us do that, make good use of AI. I don't think that's here yet, not really ready for prime time, but obviously that work is coming.
Well, that was going to be my next question, was about whether AI plays in this space today. Do we know if there's any movement in being able to sort of do language, normal language queries of this complex system information so that controllers, operators have a easier way to interact with the data? Have you seen any of that emerge in the
Chuck is
FDD?
going to be closer to that than me.
I personally have not. It's been my experience so far that AI requires adult supervision, but I would say that most of the platforms now that are in the upper levels of FDD are using AI to some form or another. And so to what active level they're actively doing that, I don't know. But I would say that usually if you have a good set of rules, it's going to cover most of what you need. AI has a little ways to go before it's going to decipher the efficiency of one of Jim's thermal efficiency projects, just because there's really a lot going on. And I think perhaps one of the things I see about AI is that they get better with understanding. So I know that the AI that I interact with, it begins to understand where I'm going and how I'm thinking. And once I make the major corrections on things that's just completely got wrong, then it gets better. And I suspect that FED is going to continue to evolve that way as well.
That'll be exciting to see how that emerges.
Certainly will.
And not at all scary.
So if you're a facilities operator and you have a mix of pneumatic and DDC controls in your facility, and you're trying to think about what's the best investment that I can make to improve the performance of my building, where should their attention go? Because you mentioned, Chuck, that there are some tools out there that can help optimize pneumatic systems. Is the attention best placed on upgrading the pneumatic controls and pneumatic controlled areas, or is it on digitizing what you can and getting an FDD system? Like where would I start?
That's a great question, and thank you for asking that. And that's happened a lot. There's a lot of systems out there that are currently a mix. Some of them are still running Rainbirds, and so it's across the board. In my experience, I would start with the biggest consumers of power, and so that's going to be your main plant systems, your chilled water system, your hot water systems. You have to have visibility and control of those systems, and those are usually fairly easy retrofits. The next level would be, your zone air handlers, and then down to your zone levels. And when you retrofit these, you don't have to do a complete retrofit. In other words, most systems have pneumatic controllers. The DDC systems have pneumatic controllers that will take your pneumatic receiver controller, if you will, the thing that you have to calibrate every time the humidity changes, and convert that to DDC, and it'll still pneumatically actuate your actuators. It's an easier way to go initially. It will save you some costs. The same as I mentioned for the pneumatic thermostats, that those also come in wireless. And by the way, wireless, there's been a protocol out for some time. It's called Zigbee, and Zigbee is a daisy chain protocol where it passes data from one thermostat to the other. So you don't have to put routers throughout your whole building. You can just put these thermostats in, and then they just tend to work. So for VAVs, where it's a kind of a long payback to retrofit a VAV completely, you can put these pneumatic thermostats in, and you have some visibility. A lot of times those will have also an analog input or a binary input where somebody can request occupancy, or you can put a temperature sensor in there so that you can kind of see what your box is doing in case you have a failed hot water valve. And so there's a way to step through these things. But to answer the question simply, I would say start at the top, get your biggest consumers, your chill water plant, your hot water plant, then your air handlers, and then your zone levels, and work your way down. But it starts with a plan, that's for sure.
I would add, if you think about all those advanced strategies, the energy conservation measures that Kevin talked about, those aren't pneumatic measures. They're not going to happen that way. So you really do need to get to the point of use as well. It all ends up mattering. I agree with Chuck. You start in the plant, but until you can get down to the zone level, you're limited on the overall effectiveness you can have. But then you also have to have the mechanical systems that can respond properly. So I mean, it's a complex problem to upgrade a really old building with lots of old controls, but it is the only way to really make the progress.
So I'm curious, one of the challenges that I know some of our clients face when they put in these FDD systems is, you were talking about, like alarm prioritization and alarm fatigue. And I think a lot of those FDD applications are not thoughtfully deployed to avoid those kinds of problems. You had a little bit about that in there in your presentation, Chuck, but I'm curious if you and Kevin can talk a little bit more about how to make sure an FDD system is properly deployed so that it can be effective without creating alarm fatigue.
I would say typically when I do a DDC system, I will suppress alarms at that level. Most of the FDD systems now will automatically suppress alarms. For example, if the chiller goes down, it's not going to fault all of your air handlers for having a high supply temperature. So that should be a standard, and that's something that should be queried. And I'm sure that Kevin has a little more information on that.
Yeah, that's a really good question, Christina, because a lot of times the way these are set up, they come across as an engineer's tool as opposed to a facility operator's tool, because there's so much data. And the promise is you look at these faults and the system can direct you towards the potential cause, like a root cause analysis. But that's the promise. It doesn't always end up that way. So you end up with all these errors, all these faults, and you go, well, what is truly causing it? And that's a difficult part of it. It takes a lot of forethought into how the system is designed and understanding, okay, if you're getting this fault over here, what are the potential causes? That involves the design team heavily to help who's ever implementing that FDD system understand how it works and how the causation, where the causation could be coming from. It's a really difficult process to do it right. I think, like what Chuck said, some of the low-hanging fruit as far as alarm suppression and prioritization just through filtering is the stuff that's easier to implement and has immediate payoff. Getting to some of these very advanced diagnostics is a long road, but if you get there, it's very valuable.
And the last thing I would mention also is if you have a plant like Jim just gave us a demonstration of, you're not going to get an out-of-the-box FDD solution for that particular system. So it's going to require a little bit of coordination with the design engineers and the FDD solution provider.
Yeah, that's a really good point. There's a lot of things we do on every building. So we have this collective consciousness of understanding how to approach those things. And those are the sorts of things that are a little bit easier to implement these advanced controls for and these advanced FDD systems for. And then as you start to go on these more custom systems, this came from one or two people's brains, and you have to share that understanding. And that takes a lot more to really get that to an advanced state. So starting with things that are on every building, like terminal units and air handling units, at least simple ones, make a lot of sense for trying to advance your controls and your reset strategies.
Great. Well, I really enjoyed our conversation today. Thank you so much for participating and leading the conversation, all three of you. It's been fun. And I learned a lot. So I hope our audience learned a lot too in the process. So our next, save the date for our next speaker. It'll be November 18th at 8 a.m. Pacific, 11 Eastern. We're going to hear from Swarthmore College's decarbonization journey with Andy Fike, who is the facilities executive at Swarthmore. They are undertaking their transition to an electric future and have made a real progress on implementing their plan. I think it'll be really interesting, regardless of what sector you participate in, to see what a campus solution looks like for implementation. So I hope you'll all join us to learn about this interesting project next month. Thank you so much. Have a wonderful day, and I hope you all enjoy this beautiful fall.